we go. All right. Did everyone hear that little warning? Nod if you heard that little warning. This meeting is being recorded. Okay, good. Dr. Peterman took you through the basics of cable-stayed bridge analysis on Monday and analyzed a relatively simple but reasonably scaled cable-stayed bridge with uniform load applied to it. The diagram that's on the screen right now shows, let's see, so let me find, there's this annotate feature, right? Is that there? Okay, so the version that's on the screen right now shows the same bridge, but with one important difference. I have split the load into two parts, 0.45 kips per foot, which I've applied to the entire bridge. Let's imagine that as being basically the dead load. And then another 0.55 kips per foot that we can imagine being live load. And I've put that only on the main or central span of the bridge, all right? And Kara, can you see my cursor as I'm trying to point at things here?
Yes.
Okay, thanks. So that's the sort of setup of this problem. What I want us to do is to be able to calculate the load or the force in cable 2 here and cable 1 here to get an idea of how non-uniform live load affects the bridge, and then also to see how those non-uniform loads propagate into the tower itself. I'm just going to check something here. I'm going to mute everyone because I hear a little bit of feedback coming through, and then Dr. Peterman, you should unmute yourself, okay? But no one besides Dr. Peterman for now should be unmuted. Let's see, I'm having trouble with that. What if I exit annotate? There we go. Mute all. Okay, and now Dr. Peterman, you should unmute yourself, please.
Done.
Good, thank you. And I'm gonna go back into annotate. All right, so that is the problem setup. And you can't, I see. If you're in annotate, you can't move to the next slide. Okay. Cable 2, which is the cable right here, that will have the same force as was calculated on Monday. It's actually on the other side of the bridge from the one you looked at Monday based on the notes I saw, but the cable force in 2 is gonna be the same, 202 kips. So that's T2. So no recap there needed. But cable 1, we'd like to look at a little bit more carefully. So I would like you to take a moment now, and I hope you have a piece of paper with you, because I'd like you to look at this point right here, where cable 1 attaches to the deck, and I'd like you to draw the set of forces and their vectors that are acting at that point, okay? So think about the load acting on the bridge, the cable, and the deck, and what forces could be acting at that point. And we'll take a minute to do that. All right, take 10 more seconds. I see from Daniel leaning up to the screen that the text is pretty small there in the diagram, which is probably true. Okay, so I hope you were at least able to get arrows down. In order to get them labeled, there was some calculation needed based on the loads. I'm not too terribly worried if you didn't get that written down, but here's where I hope you will have ended up. if we look at that point, we have the cable tension T1 acting upwards and to the right. We have the weight, the load acting downwards. And we can calculate that value. This is load, which is only the dead load in this case on that span, and the tributary area of that cable, and we get a number. And then also, which is really important, right? One of the key features of cable stayed bridges is that we have this deck compression. So this tension comes out to be 48 kips if you go through the sum of the forces in the y direction calculation. If you did sum of the forces in the x direction, you would get the deck compression. Okay, that allows us to get tensions T1 and T2. In my slides, I've broken up the notes, but then at the end of each kind of little section, I've put the full page of notes there so that you'll have access to it all in one screen. Okay, so now I'd like you to do a little bit more work. We have T1 and T2, 202 kips at T2 and 48 kips at T1. There we go. And I'd now like you to take a chance and take a minute and draw the free body diagram for the tower, okay? Including the cable 1 and 2 forces that we have geometry and numbers for, and the base reactions of the tower. So take a minute to do that, please.
Professor Awadi?
Yes.
I'm taking notes myself here, and I was wondering if you could just pause on the screen for a little bit so I can catch up with what you have on the screen.
Yep, so this will be up for at least the minute that I'm asking people to draw the free body diagram, and we can certainly give a little bit longer than that. All right, let's take 10 more seconds. I don't mean to put pressure on you, but just to give you an idea of where we're headed in the next few moments. All right, and I'm gonna go ahead, and I realize, as Dr. Peterman pointed out, that when you have notes prepared like this, feeling like you have to copy it all down is challenging. Remember, this is all gonna get posted to Moodle, so you'll have access to my notes. So that free body diagram looks like that, all right? And I hope that many of you got that down on your pieces of paper. The total tower height is 180 feet. Here are 202 and 48 kips. They're each acting at 45 degrees from the horizontal, and the tower is fully fixed at the base, so a vertical reaction, a bending moment, and a horizontal reaction. I'm gonna go ahead, but if there are any questions about that, feel free to put something in the chat, and I'm happy to come back to it. The purpose of the free body diagram, do we need to account for the thrust from the deck?
There's a question.
So do we need to
Professor Awadi, there's a question.
Do we need to account for the thrust from the deck is the question. And it's not going to appear on this free body diagram because I'm assuming that the deck is not physically attached to the tower, all right? It might be depending on the detailing, but here we're going to neglect that and assume that the deck essentially passes past the tower and is connected only to the cables. All right, the purpose of the free body diagram is to do some equilibrium calculations, and particularly I'm interested in the vertical reaction. So that's 176 kips. That's important because that is a compressive load that would be used to design a tower. You need cross-sectional area to resist that compressive thrust. And you also need to make sure the tower doesn't buckle, all right? It's basically a very tall, slender column with a point load applied to the top. More interesting for us, I think, is the bending moment. So we can take some of the bending moments about the base of the tower right here. This will be our moment equilibrium equation. 48 kips and 202 kips, they're moment arms and the sine trigonometry here. And we get a bending moment of almost 20,000 kip feet. It's perfectly reasonable that that number doesn't have much meaning to you in terms of its magnitude. It's pretty big. And the importance is that the importance of that number is that it is also something for which the tower will need to be designed for. So the tower is effectively a column. It has a point load applied at the top vertically, but it also, because the two cable tensions are different from one another, has a resultant lateral force, in this case pointing to the right. And if we're going to design that column, we have to design it to resist both the vertical load and the bending load or bending moment that is applied to it. All right. That's what I wanted to say there. Yeah, go ahead. Yes.
You're breaking up a little bit during your discussion of designing for that moment. So I was wondering if you could repeat it.
Sure. So the basic idea of why this number is important is because the tower is a column, and columns need to be designed to resist both vertical compressive loads and also bending moments. So if you were to choose the cross section of the tower and try to design it, you'd have to design it for combined bending and axial stresses. I'm going to go ahead and without doing the full calculation here, I want to point out that we can also use this configuration to calculate deflections of the tower, because the tower is basically just a vertical cantilever with a horizontal point load applied at the top. In this case, it's 109 kips, which is the resultant horizontal force of the 202 and 48 kips. And it's a cantilever with point load. PL cubed over 3EI is our equation. This might be, in fact, a way that we would design the tower. We might have an allowable displacement, choose a material, concrete or steel, that gives us elastic modulus, and then choose a cross section that gives us a big enough moment of inertia to limit the deflections. That is what I wanted to do in terms of cable-stayed bridges and to talk about non-uniform loading. So I'm gonna breathe for a few seconds here, 10, 15 seconds, and allow anyone to type into chat if they have something they want me to go over. Okay. That is that full set of notes, all right? And again, these will get posted. So let's move on to suspension bridges. I took the same geometry as Dr. Peterman used for the cable-stayed bridge here, same spans, same tower heights, but instead of cable stays, I drew in a suspension bridge cable, all right? And I assumed this 1 kip per foot loading again. Where I want to start with is this. I want you to draw a free body diagram for the tower, including cable 1 and 2 forces. Let's see, that's not right. What do I want you to do? I want you to draw a free body diagram for the entire bridge. The entire bridge, including tower base forces and anchorage forces. And you can start on that if you like, but let me also grab this image and paste it here. And that way you can see what to do. All right, so take a moment and see if you can construct that free body diagram for the entire suspension bridge. A very rough sketch will suffice here to get the free body diagram done. Let's take 10 more. Okay, what I hope you got to was something that looks like that. No numbers here, but each of the towers is fully fixed at the base, so we get vertical, horizontal, and moment reactions. And then I made an assumption here, which I'll detail later on, which is that these cables in the side spans or back spans come to be perfectly horizontal by the time they reach the anchorage. And if they come to be perfectly horizontal, the anchorage force will be solely horizontal, H1 and H4 over here. So that's our free body diagram of the overall suspension bridge. And here are the assumptions. So parabolic cable geometry. So if I wanted to understand the geometry of this main span cable or these back span cables, I need to go to the math of what a parabola looks like. And we did that for arches. So I refer you back to the arch notes there. Cables never carry any bending moment. That's just a rule of how we analyze cables. And that in this particular configuration, I've assumed that the cable sag is all the way down to the deck here. The geometry can get more complicated and subtle, but this is a realistic, if simplified, version of suspension bridge geometry. Okay, and that is that full page of notes available for you. All right, I want to then take you through analysis of suspension bridges. And our main goal in analyzing suspension bridges is going to be get the main cable force. All right, that's really what we're going to talk about in terms of analysis today. This is the Brooklyn Bridge, as you can see here, and then this is a free body diagram that's kind of layered on top of the Brooklyn Bridge, some gravity load, which could be dead and live combined, cable tensions, again, I'm assuming perfectly horizontal, and then a tower base reaction vertically here. I've neglected both the horizontal and moment parts of the tower base reaction for suspension bridge, and that's a fair enough assumption for the level of analysis and design that we're going to want to do. In order to get the main cable force, I need to make some section cuts, right? This is what we do when we do internal forces of structures. We make section cuts. And the section cuts I want to make are one at midspan, that's here, and another one, in this case, just to the left of the leftmost tower, all right? And these red arrows indicate forces that are acting, tower base reaction, cable tension, and cable tension. And then the main span length and the cable sag are the key geometric parameters. I apologize for that weird green that those arrows are in. These slides used to be on a black background. It looked better against black, but in fiddling around with PowerPoint today, they went to white background, and I didn't have time to change those colors. So I hope they're at least marginally legible. Okay, free body diagram. I can put some symbols in. Let's call H the cable force, VB the vertical reaction, W the load, D the cable sag, and L/2 the half span. We're going to keep that diagram up there so it's not going away. And I can use moment equilibrium to get cable forces here. I want to look at the top of the tower, and I want to take moment equilibrium about that point, okay? And if I take moment equilibrium about that point, well, VB has no moment arm, and H at the tower top has no moment arm. So the only two quantities that need to appear are the load, W, and the force in the cable at midspan. If I write those down, and the colors kind of match up here, H times D, that's the moment contribution of that cable force, and WL squared over 8 is the moment contribution of the load here. W times L over 2 is the load, and then the moment arm is L/4. We have to remember here that we're dealing with only half of the main span. All right, and if you solve this, you get that H, the force in the cable, is WL squared over 8D. That is kind of a magic equation for suspension bridge analysis. It actually is identical to the equation for thrust or compressive force at the crown, at the peak of an arch. Because as we remember from several weeks ago, arches and suspension bridges are the same thing, same structure, just with a negative sign in front of them, all right? So this is the equation that we've just developed and that we will use to calculate force in the main cable of a suspension bridge. And I want to spend a little bit more time talking about what that equation means, all right? Same diagram here. The equation here, H is WL squared over 8D. W is the load, so that's nature acting on the structure. L, the span here, that's really the size of the bridge. That's how big the structure is, right? And that sort of has some assumption that if the bridge gets larger, the towers grow in height kind of at the same rate that the span grows in length. But L is basically size. R is this quantity right here, which is the ratio of the span to the cable sag. And that I'm calling here a sense of the form of the bridge. If you go out and look at different suspension bridges, you'll see that some of them have really tall towers and some of them have quite low towers. The Brooklyn Bridge has relatively low towers. The Golden Gate Bridge, for example, has very high towers compared to the span. So R, in a sense, is a measure of the form of the structure. And then H is what I'm calling the function of the structure. That's what the bridge is there to do. It's there to carry load through its main cables to the ground. So if I make a substitution for R here, I wind up with a version of my equation that is H equals WLR over 8. And the way I would love for you to think about this is that the bridge is a system. And the bridge acts as a system to take load W and transform it into H, force in the main cable. And it does that through its size and through its form R. This brings us back to Billington's idea about form and function, right? The idea that the engineer, the designer, is actually in charge of what's going on in the structure, is in charge of the forces in the structure. So W comes from nature, comes from traffic, whatever, weight of materials, right? But we don't have much control over that. But the designer does have control over R and L. The designer, to some extent, can choose the length of the main span, and the designer largely can choose height of towers relative to span. So the designer can actually exercise a lot of control over what the final force is that will be in the main cable of the suspension bridge. And it's, of course, that force that then has to be resisted by the steel in the main cables. All right. So this slide, I think, is basically the end of our analysis of suspension bridges for today. And so I just want to say again that what I want you to take away from this is first, I think that using relatively simple analysis methods, just equilibrium and section cuts, we were able to figure out what the forces are in the main cable of a suspension bridge. And second, that it's possible to think about this relatively simple equation, all right, and its new form down here. It's possible to think about that equation, which just comes from statics, as really being an equation that tells us how a structural engineering designer can be in charge of how forces are flowing through their structure into the ground. I do have one more slide, and these are some mast hand models that show how form can affect force. So suspension bridges here, same spans, same geometry, except that the tower is taller in the bottom model. And what I hope you can see is that the taller the tower is, the smaller the compressive force is in the main cable. All right, here, this sort of pale blue bar here, the width of that pale blue bar indicates how much tensile force there is in the main cable. And these red bars indicate how much compressive force there is in the tower. So this is just another graphical view of how changing the form of the structure actually affects the forces that are acting in that structure. All right. So the calculations that you saw on Monday with Dr. Peterman for cable-stayed bridges under uniform load, cable-stayed bridges with non-uniform load today that I showed you, and then the basics of suspension bridge calculation, main cable calculation. These are the kinds of things we're going to want you to be able to do in your analysis and design assignments. It's all relatively straightforward in terms of the math. Really, there's nothing here that wouldn't be at home in a sophomore level statics class. But as we did with arches and as we did with light frame structures, what we're going to do is ask you to take these relatively simple analysis tools and apply them to actually be creative with the solution to real design problems. That's what I have. Dr. Peterman and I have agreed to try to keep these online meetings pretty tight. I know from very deep personal experience that it's hard to keep paying attention when you're just looking at your computer screen. So that's what I have for today. Why don't I take at least 20, 30 seconds and allow you guys to chew on that for a moment and type any questions into chat or even just type into chat that you want to ask a question verbally, and we will discuss as needed.
Professor Arwady, we have a little bit of feedback
Okay.
in the chat.
Yes.
Do you want to take a look?
Yes, I see that. And Andrew Fiore asks if I can go slower or post the slides ahead of time. Yes, I think posting the slides ahead of time sounds pretty good. Without being able to be with all of you, it's really hard to gauge how quickly note-taking is happening. But I think, Andrew, that's a very reasonable request. And so for future analysis classes, we will get the slides posted ahead of time. And that'll allow you to kind of take notes. If you print them out, take notes on the sheet or type on the screen or something like that. But that's a good suggestion. Thank you. We'll do that. Yes, Hernan, feel free to go ahead and unmute yourself.
Yeah, thank you, Professor. So my question is about, what about the self-weight of the cable?
Yep.
Because previously we also saw that how important it could be just the weight in the cables. And how important it will be, for example, to consider that self-weight of the cable in our calculations.
Yep. So as we did with arches, we typically, at least at our kind of level of analysis, we will typically neglect the self-weight of the cable. If you think about a large suspension bridge, such as the Brooklyn Bridge, George Washington Bridge, or so on, and you think about the dead load of the deck, the steel deck typically, or concrete box girder deck, and traffic load, the self-weight of the cable is very small. It is not small in real terms, right? I mean, these cables are huge amounts of steel and weigh tons and tons and tons. But compared to the dead load of the deck and the live load on the deck, we can reasonably safely exclude or neglect the self-weight of the cable. And that also is what allows us to assume that the cable is parabolic, because it becomes so under uniform loading.
Thank you.
I have a question, thinking ahead towards the assignment, but also thinking about the Brooklyn Bridge.
Yep.
We saw in both of our lectures that you know, statics can get us pretty far here. In a case like the Brooklyn Bridge, where you have the cable stayed in combination with the suspension bridge, can we combine the two methods of analysis to resist the load?
So Roebling didn't. Roebling analyzed the two systems independently from one another and then superimposed them structurally. In order to be able to actually do that, you get into a rather complex field of kind of nonlinear analysis. So trying to do that is really beyond what we're trying to do today. I would say if during the design exercise, if someone wanted to propose a combined cable stayed suspension bridge, one should go ahead and do it. I think that's a great idea. And what one should do then, or what a pair of people should do, is they should explain carefully their reasoning behind how load will be shared between the cable stayed system and the suspension system, and then do the two analyses separate from one another. And if someone wants to go down that road, then that's something we can definitely use the consultations next week to go over.
So speaking of consultations, there was a question on the format of the consultations that came in kind of after you started in on the analysis questions. And so I just wanted to circle back to the format at the end here. Basically, so the assignment will be posted Monday, but then when we meet on Monday, it's just to go over it and talk about the assignment with individually, and maybe you know, see if you had any questions from this past week. So even though we're posting the assignment on Monday, you're not expected to do any work on it for Monday. By Wednesday, however, you are expected to have done some thinking about it. So you will meet with us twice, Monday and Wednesday. Monday is just brainstorming with us, sort of seeding ideas. Wednesday is an opportunity for questions and feedback after you've had 2 days to think about it.
Daniel, go ahead.
So we've talked about how important, wait, actually, have we talked about it in this class? Oh God, I'm getting my classes confused now. Is there going to be a stiffness requirement
Yeah,
as part of this project?
Good question. There's not going to be. The calculation of the deflection of cable-supported structures is extremely complicated, frankly, and is really beyond undergraduate structural engineering curriculum. It's not even really possible to easily do it in computerized structural analysis without going to specialized cable-type elements. So I get you, Daniel. There is a disconnect between what we emphasized in the history of suspension bridges lectures and what we're asking you to do in the design and analysis assignments, but that just is related to the practicalities and challenges of doing deflection analysis of cable-supported structures. The sort of kernel of why it's so hard is because cables change geometry under load. And so it becomes impossible to solve for deflections on undeformed geometry. They immediately become geometrically nonlinear structures.
Sounds good. Thank you.
All right, let's call 30 seconds for any last questions, and then I think we will do our best to wrap. So I'll take a few deep breaths. I'll thank you
Have a sip of my tea.
You'll have tea.
Mhm.
And I'll thank all of you for bearing with us as we kind of do our best to keep this semester rolling along. I hope everyone out there is doing all right. I know this is a difficult time. Zoe, good. Zoe asks if there will be an analysis assignment this week. Yes, there will be, and it will be posted this evening sometime, and we'll make sure to get a Moodle mail out to everyone when it gets posted. But there will still be an analysis assignment. We will ask you probably to take pictures with your phones and upload those to Moodle for us to look at and grade. Thank you, Zoe.
Another sip of tea for last question.
Yep. Going once, going twice. Oh,
Out of tea.
Assignments, Zachary. All right, Zach. So will the assignments still be in pairs? The analysis assignment will be individual, but the design assignments we still would like you to do in pairs. We recognize that is harder to do when you're not living in the same place, but give it a shot with video conferencing and FaceTime and things like that. We hope it'll be possible. If it turns out to not work, we'll reevaluate for the future, but we'd like to have you give it a go for the design assignment, but not, excuse me, for the analysis assignment. All right, going once, going twice. All right, look for a fair amount of email from us, and we will see you on Monday of next week. Bye-bye.
Bye, everyone.